In this video, we'll be looking at solving exponential equations. Exponential equations have the variable occurring in the exponent. So we can see here there's an example of 7 to the power of x is equal to 49, and the variable that you're solving for is in the exponent. We could solve this problem of 7 to the x is equal to 49 by inspection. What you're wondering is, what power do I raise 7 to get 49? And we know that 7 squared is equal to 49, therefore x must equal to 2. So this method doesn't always work. We're not always so lucky to know the correct exponent to raise a number to get a particular result. So for example, if we were given the problem 3 to the power of x is equal to 15, there's no simple solution that results in raising 3 to a particular exponent to give us 15. For this example, it suggests rewriting the equation in logarithmic form. So we would write this as log of base 3 of 15 is equal to x. Now we can solve for x by using the change of base formula. So log of 15 divided by log of the base, which is 3, and x is equal to approximately 2.46. So you can see in this example, it worked to rewrite the exponential equation in logarithmic form and then solve for the value of x. So here are some steps to solve exponential equations. Step 1, determine if it is an exponential equation. So we need to determine, is there a variable that is in fact in the exponent? If it is an exponential equation, then we can take the log of both sides of the equation, use log properties to move the variables from the exponents, collect all the unknown variables on one side of the equation, and then use algebraic steps that we've covered in Math 145 and used a lot in this course already in order to solve for the variable. Remember that log or ln of a number is simply a number, so you would move it around just like you would move any other constant around. Let's try some examples. Solve the following exponential equations and round to 3 decimal places where appropriate. Example 1 says 10 to the power of x is equal to 2. If we take the log of both sides of this equation, so we take log of 10 to the x and log of 2. Remember, what you do to one side of the equation, you must also do to the other, which is why if we take log of one side to get the exponent out front, we must take the log of the other side of the equation as well. And now you can see that we have x times log 10 is equal to log 2. Okay, log 10, because log is already of base 10, so log base 10 of 10 is 1. And so this results in x being equal to log 2. And if we solve this to 3 decimal places, we get 0.301. Question 2 says e to the power of x is equal to 3. We could proceed with taking the log of both sides of the equation, but I'm going to take log base e, or ln, because we have a base e. Okay. On the left-hand side, our exponent comes out front. Remember, ln of e is 1, therefore x is equal to ln 3, which reduces to 1.099 when rounded to 3 decimal places. Here are some practice problems. I'm going to post the solutions to a few of them and show full solution and video to others. So pause the video, give them a try on your own, and then compare your solutions to what is posted. Keep in mind there are many correct mathematical steps that you can follow in order to solve these, so your process work may not look exactly the same. As long as it's well documented and easy to follow and correct, then you will receive full marks for your work. We see here with part A and B, we take the log of both sides of the equation, solve for x, round to 3 decimal places, and we get the following answer. Part C, you could take the log of both sides. Here I'm choosing to take ln, since we have an exponential component that has a base e. And when we solve this, we get the whole exponent comes out front, so 0.05t. Then we're left with ln e, which is 1, and log 2 on the left-hand side of the equation. Okay, so now I'm going to mark here that ln of e is equal to 1. Therefore, to solve for t, we get ln 2 divided by the coefficient 0.05 in front of t. We get 13.863 when rounded to 3 decimal places. You can always check if your solution is correct by plugging in your value of your variable that you solve for into the original equation. But note that if you sub in the rounded version of the variable, that there will be some discrepancy between the left-hand and right-hand side, whereas if you take the full unrounded solution from your calculator and plug it in for the variable, you will find that the left side is exactly equal to the right-hand side. The next equations get a little bit more complicated, as the exponent is not simply just a single variable. We actually have a linear expression as part of our exponent. Now, taking the log of both sides of the equation, the exponent will come out front, and we have log 5, and on the right-hand side, log of 7.08. When I brought the exponent out front, you can see that I put brackets around it because all of the exponents, so 2x minus 3, is multiplied by log 5. Now, to solve this equation, we want to divide both sides of the equation by log 5. So the left-hand side of the equation, our log 5 cancels out. We are left with 2x minus 3 is equal to log of 7.08 divided by log 5. And now we need to solve for x. So to solve for x, we bring the 3 to the other side of the equation. And yeah, by adding 3 to both sides. And last but not least, we divide the entire thing, the entire equation on both sides, by 2. Now we solve for x. We find that x is equal to 2.018 when rounded to 3 decimal places. In part E, I started off by dividing both sides of the equation by 4,000 to get the exponential portion of the problem on its own. Then I took the log of both sides to bring the exponent out front. And then lastly, divided both sides of the equation by 1.08 to solve for x. In part F, we start by taking the log of both sides of the equation to bring both the exponents out front of the logs. Now, if we expand out both sides of the equation, we get x times log of 3.25 plus 2 times log of 3.25 is equal to 3x times log of 1.44 minus log of 1.44. Now we have two terms that have variable x and another two terms that are just constant. Bringing both terms with an x to the left-hand side of the equation, we get x log 3.25 minus 3x times log of 1.44, and everything else to the other side of the equation, we get minus 2 log of 3.25 minus log of 1.44. Now, as we did with our factoring unit in Module 4, We can factor out x to the left-hand side, and we're left with log of 3.25 minus 3 times log of 1.44. And the other side of the equation remains the same. Now, this equation really does not look straightforward and doesn't look like something you would enjoy calculating. But if you proceed carefully and evaluate it sort of slowly, you can simplify this just all into one number. So we have to divide both sides of the equation by log of 3.25 minus 3 log of 1.44. Make sure if you're evaluating this in your calculator all in one step, you need to put brackets around the top and bottom of your expression. So now we can evaluate this. You end up finding that x is equal to negative 32.126666916 approximately. When rounded to 3 decimal places, negative 32.127. So part F is definitely one of the more complicated problems that you would end up seeing. Let's take a look at part G together. We have that 10 to the power of 5x is equal to 2 times 10 to the power of 2x. In part E, we had a coefficient like this 2 here, and we divided both sides of the equation by 2 before proceeding with taking the log of both sides. But in this problem, you're unable to do so, because if we divide by 2, you could divide by 2, but it won't simplify to just be a constant on one side of the equation. We have exponential on both sides. So what we're going to do is take the log of both sides right away and use some properties of logs to solve for x. So we get log of base 10 of 10 to the power of 5x is equal to log of 2 multiplied by 10 to the power of 2x. Now we can simplify this. So we're first going to use the product rule where we get the sum of 2 logs. So log of 2 plus the log of 10 to the power of 2x. And on the left-hand side, we still have the log of 10 to the power of 5x. Okay, so what we can see here is that if we simplify this, we get 5x times log 10 is equal to log 2 plus 2x times log of 10. Recall log of 10 is just equal to 1. Therefore, this simplifies to 1, and so does this. So we can rewrite this as 5x minus 2x is equal to log of 2. Now simplifying the left side, we get 3x is equal to log 2, and therefore x is equal to log of 2 divided by 3. One thing that I should make sure I emphasize is that you're just taking the log of 2 and then dividing it by 3. We're not taking the log of 2 over 3. That would give us a very different result. This simplifies to 0.100 when rounded to 3 decimal places. While I was solving these problems, I took the full unrounded value from my calculator, substituted it into the original equation, and checked that the left-hand side equaled the right-hand side. I didn't write that full check out, but I did it to ensure that my answer was correct. I hope you take the time to check yours as well. Another way that you can check your solution is by graphing both the left-hand side and the right-hand side of the equation and solving for the point of intersection. For example, in the last problem, we had 10 to the power of 5x, and that was equal to 2 times 10 to the power of 2x. So if we graph both of these equations, we can see, so both sides of the equation, in fact, we can see there's a point of intersection here. And what we are looking for is the value of x where these graphs intersect. If we zoom in and select the point of intersection, we can see that this x value, when rounded to 3 decimal places, is 0.100, just like we solved for algebraically. So that's another way that you can find your point of intersection, or the value of x that makes both sides of the equation equal.